Autos. So welcome back from the brainstorming sessions. Welcome to the next session where we will talk about the structure of digital twins and the standards, potential standards for digital twins. I introduced myself already. My name is André Borrmann. I'm heading the chair of computational modeling and simulation here at the Technical University of Munich, and I will speak about the structure of digital twins. That's the topic that Johannes assigned to me. Before I talk about this, I will shortly introduce the Leonhard Obermeyer Center, which is the environment we are working on here at UM. The Leonhard Obermeyer Center is the TUM Center of Digital Methods for the Built Environment, consisting of 6 TUM groups, which is Architectural Informatics led by Professor Petzold, Computational Modeling and Simulation, that's my group. We have Numerical Simulation led by Professor Rank, the area of Geographic Information Systems led by Professor Kolbe, Photogrammetry led by Professor Uwe Stiller, who is here also. Then recently Professor Nübel joined our center with the group for Construction Process Management. So we have a pretty complete range of expertise with respect to the digital methods of the built environment. And of course, the digital twin for the built environment is a very hot topic for us, and we are working on this as well. In total, we are more than 60 researchers in our center, which makes us one of the biggest centers in this regard in Europe. We intensively collaborate with the construction industry and also the software industry. Here on the right-hand side, you see our premium members in the upper part, the associate members in the middle part, and in the lower part, you see the non-profit organizations and the governmental institutions that we are working with closely together. Now I want to talk about the digital twin, actually the structure of the digital twin, but I would like to start to talk about the definition, because it's always good to start with a definition. We heard a lot of definitions this morning already. When I did my research to prepare this talk, I came across the fact that actually there's no commonly agreed, detailed and precise definition of the term digital twin. The question is it needed? Maybe we don't need it. There is at least a commonly agreed baseline across the different definitions I found. So everyone says it is a comprehensive digital representation of a physical entity. It is a replica. Some say it's a really detailed digital representation, a digital copy. Others say no, it's an abstraction, so there is some room for improvement, for interpretation. All agree that it is used throughout the life cycle of the physical entity, and it must be kept up to date, so that's a key feature. And it should allow to learn across the life cycle, across also different individual physical entities, to learn about their behavior. The entire rest, all the details, really depends on the purpose of the digital twin. So let's talk about the purpose. The digital twin should be used across the entire life cycle, that's clear. So for built facilities, that's typically we start with conceptual design, then we go to detailed design, then the very important phase of the constructing the built facility, and then the even more important phase and very long phase of operation, where the digital twin really comes into play. Then we have the digital twin can be used for demolition also, and for any modification of the real world entity. In these different phases, we will have typical use cases. So for example, in the conceptual design, we will use the digital twin for life cycle assessment, for usability studies, for assessing different options. During the detailed design, we will use it for coordination, for cost estimation, for simulations. Then in the construction phase, we will use it maybe for prefabrication. Very sure we will use it for process simulation, for steering, logistics, for doing progress monitoring of the construction, and for controlling, most importantly, for controlling the quality of the facility that we built. Then, as I said, the very important part of the operation, where we use the digital twin for condition assessment, and this is then the basis for deciding on maintenance and repair. For demolition, we might decide what we can recycle, and for modification, we decide redesign and retrofitting. I said it before, it's actually not only one digital twin, but many. So we will create for many physical entities, many digital twins, to learn more about the behavior of the structure as a whole. Now, I brought along three different examples for digital twins. The first example is a very large project here in Munich, currently being conducted. It's the second main subway track that is currently being constructed in the inner city of Munich. It's crossing the entire inner city of Munich. It's a quite complex project, and we created this digital replica of the project. You might argue that this is not a digital twin. Others say that's a digital twin of the future. It's not existing right now, but it will exist in the future. What it does not provide yet is that it can be updated. But of course, that's a good basis for updating the digital twin during the operational phase. So that's the first example. Next example is this digital twin. It's a digital twin of a construction site. In this case, we captured the construction site using photogrammetry. We created a point cloud, and here the point cloud itself is the digital twin actually. And what is different here is that now we have the dynamics in the model, so the dynamics of the construction site. We captured this point cloud in regular intervals, so we really followed the construction site and created a dynamic digital twin, which comes closer to the actual definition of a digital twin. So you can see how the digital twin evolves with its physical counterpart. It's really growing like the building is growing as well. So now the point cloud can be seen as the digital twin. However, in most cases we need more information, so we need to interpret and process the point cloud. And in this case, we did so, and we matched the point cloud against the BIM model, and we identified where the construction site was in schedule and where it was behind schedule. So this is this kind of high-level information that we actually want to have from a digital twin. Then a third example, again completely different. This is a quite famous example of a 3D printed bridge where many researchers, especially in the UK, have been involved. You see on the right-hand side, in the upper part, you see the physical object that has been produced. It's equipped with a large number of sensors. On the left-hand side, you see a numerical model, and in the lower part, on the right-hand side, you see how the numerical model is connected to the sensors. So in this case, really the physical behavior, the structural behavior of the real-world entity is completely mirrored into the digital twin. That's another interpretation of the term digital twin. So in essence, defining the purpose of the digital twin is key for any meaningful discussion on digital twins. So I talked about typical purposes already. Now, what are the typical components on the other hand side? Typical digital twin components are geometry, semantics, of course sensor data, maybe also a physics model. Time is an important component, and maybe also predictions. So from this, I tried to sketch generic structure of digital twin, because my objective was to talk about the structure of a digital twin. It's very much dependent on the purpose of the digital twin, but I tried, so I came up with this generic view. So in my point of view, in the core, the digital twin consists of a number of interconnected models representing geometry, semantics, and physics they are developing over time. Of course, we have sensors. The raw sensor data in many cases will not be of direct use for the digital twin, so it must be processed before its data can be fed into the different models. We will have a learning component, maybe many learning components, to identify patterns across the different digital twins. All this must be based on well-defined data structures. Most likely that will be linked data structures. We come back later to this. And I added also on top visualization because Mark was emphasizing this morning, so I added this to this figure here. So let's have a closer look on the individual components. So first, geometry. Geometry is difficult. I say some digital twins will not require geometry at all. So in the Arup white paper that was distributed, they talk about the digital twin of the Google Nest. That's a very simple digital twin where the sensor, the controller, and the room temperature are set into relation. Very simple, no geometry is required at all. Others digital twins will require only 2D geometry. For example, if we have the digital twin of an entire road network, of an entire state, then of course you will not have a very precise 3D description of the entire roads, but maybe here 2D representations are completely sufficient. And we have these kind of systems already for monitoring the condition of the roads. Some digital twins will need point clouds and will directly operate on the point clouds. Others will work with surface data. Others, and many of them, will require volume models. Again, we have the option to use different kind of volume representations. We can use BREP models, we can use octree models. Again, it depends very much on the purpose. What I really would like to emphasize is that the level of detail really, again, depends on the purpose. It's not at all clear that a digital twin must be as detailed as possible. A model is always an abstraction of the reality, and so is the digital twin. Also, the digital twin is an abstraction of reality. In many cases, we have to capture geometry. In many cases, we don't capture the full life cycle, starting from design to construction to going into operation. But many facilities already exist, so we have to capture geometry. We talked about this already this morning. We have a typical pipeline starting from sensing, using different approaches, laser scanning, photogrammetry, and other approaches. We will most likely come up with a point cloud. Sometimes we can stop there and directly work with the point cloud for the digital twin. In many cases, we will further process it and come up with the surface model and then create the volume model. Sometimes we have to go beyond the volume model. And here I have one example of a project at my group where we try to create the digital twin of railway facilities. We have the point cloud of the railway. What we want to have is a high-level description of the alignment of the individual rails. So we want to have information about the straight segments, the transition curves, and the arc segments, including their parameters, because this is the engineering information that we actually need. And we have to process the point cloud to get this kind of information using, for example, principal component analysis. That brings us to the next important topic, which is semantics. Most digital twins will not rely only on geometry. Essentially, every high-level representation requires a solid description of the semantics. Typically, we will use some kind of object-oriented representation. We can achieve this object-oriented representation using conventional modeling techniques, or we can use more modern approaches like, for example, ontology modeling. I think that Jakob will talk about this in more detail in the next talk. There are a large number of standards available. Also, this will be covered by Jakob. And these standards actually provide a very good basis for the digital twin. But of course, they will have to be extended. Also, we have to think about whether the internal representation of the digital twin at your digital twin platform will maybe differ from these standards. It will be most likely be simpler, but it will maybe also be more extensive because you will cover other aspects, other domains than the standard covers. In most cases, we will use linked data approaches because we have many different domains that have to be linked together. And the experience that we have from our work in Building Smart and elsewhere is that big monolithic models are really hard to achieve. So it makes more sense to have individual domain-specific models that have to be linked. But I have to say that linking itself is also a challenge. It's not as easy as it sounds. Again, in many cases in the built environment, we have to capture the semantics from the reality. So we may use techniques like semantic enrichment introduced by Raphael. Here we can distinguish different methods. We can use rule-based inference, or we can use any kind of machine learning approaches. Both of it has been shown to be successful. For example, on the right-hand side, we identified the formwork on construction sites using machine learning. Another example is again from our railway project. Here we use machine learning to identify objects in the railways, equipment objects, using the video and machine learning. And this is, of course, an important component of the digital twin, including also the semantics. So here semantics is much more important than the actual geometry. Of course, the location of these elements is important. Then we have another good source, especially in the built environment, which is drawings. There are many, many drawings out there. And of course, we should use them as a source to populate our digital twin. But we have to make sure that they are really correct, because this is really not a digital twin. This is maybe not even a twin. It might be not correct what is in the drawings. So we have to be very careful what we take over into our digital twin representation. Another very important component, and we heard about this very often this morning, is sensor data. For linking reality with the digital twin, we need sensor data. It is essential to make our digital twin really a living representation. But Mark also emphasized that the raw data itself, the sensor data itself, is in many cases meaningless. So we have to transform the raw data into some kind of meaningful representation. And I brought along this well-known pyramid of data, information, knowledge, and wisdom, where we try to get as much as possible out of the data. If we get it to knowledge, that's already quite good. If we achieve even wisdom, that's even better. Again, the question of the update rate is important, and this again depends very much on the domain and the purpose of your digital twin. Many think that a digital twin is always updated in real time, but of course that's not necessary in all cases. When we think about road networks, for example, then it wouldn't make sense to update the condition of the road every second. Instead, it would be sufficient to have it every year, maybe every 2 years, something like this. What, however, is really important for most digital twins is the modeling of the physics. The physics models describe the interaction of the real world entity with its physical environment. And of course, we want to mirror that into the digital twin. There are many physical models out there, many physical phenomena. It wouldn't make sense to really list all of them. I just listed some. Sometimes deformation is important, sometimes stresses are important, sometimes temperature is important. It really depends on the purpose of your digital twin. I brought along one example of a very old facility. That's actually a building from the Greeks, a Greek temple. This has been captured using photogrammetry, and the point cloud has been generated. And on the basis of this point cloud, a computation mesh has been generated. In this case, it's an octree. And this octree has then been used for calculating the structural behavior. So the stresses and the deformations have been calculated. And on this basis, you can do statements on the stability of the structure. So again, a very typical use case of digital twins. Another important component is time, prediction, and learning. So it's very clear that a digital twin has to be able to represent development over time. It has to evolve with the real-world twin. Again, we have to distinguish the modeling of time with respect to continuous versus discrete. Very often we want to look back to say something about the history of a building or any other facility. But what is even more interesting is to look ahead and to do a prediction of the future. So for this, we will typically use all the sensor data, but we will most likely also use the physics models. So that's very important here. And what we also do in many digital twins is that we adopt our models over time. So we change the parameters according to what we measure, according to the sensor data, which then also helps us to improve the reliability of our models. That's also an important aspect of the digital twins. And then we have the cross-twin learning aspect. So we will do the entire exercise not only once, but for many different digital twins. We will capture a lot of data of these different entities, try to find patterns, and in the end try to improve design, try to improve operation or maintenance, because that's essentially the final goal of having digital twins. So to conclude, I must say that the structure on the digital twin, which was the title of my talk, really depends on the purpose. It's really hard to do any generic statements on the structure of the digital twin. There is definitely no one fits all for all the digital twins. We have seen some important ingredients. Essentially, geometry is very often an important ingredient. We have seen semantics is important. Physics might be a very important part of the digital twin. Sensor data, processing of sensor data. What I really would like to emphasize is that we need definitely well-defined data structures, and I totally agree with what has been said this morning, that most of them should be standardized. They should be harmonized also across different companies, across different institutions. And I would also like to emphasize that for me, BIM and digital twins are actually twins. They are not, from my point of view, not really contradicting, but instead we can very likely base our work on digital twins, on building information modeling, which provides a lot with respect to geometry and semantics already. And of course, we have to extend that to capture all the extra elements of digital twins. So thank you for listening, and I think we have 5 minutes for questions. There's one.
In other industries, my impression is that when you have something that costs a lot, and sometimes these models can cost a lot, you want to do that only when you have the ability to use it for multiple things, rather than just a single use case. Although it's my understanding here, you're kind of recommending the opposite, which is I'd like to have purpose-based twins, i.e. focusing on a specific purpose.
No, maybe this was a misunderstanding. Actually, what I'm saying is the structure depends on the purpose. But of course, normally and you are completely right, we will try to capture or to cover as many of these use cases as possible. So then, of course, the structure of the digital twin will be different, slightly different, than when you focus only on one specific aspect. So, I tried to make this clear when I talked about progress monitoring. In this case, the digital twin of the construction site might be only a point cloud and nothing else. But if you want to use it for condition assessment, maintenance, repair, we need extra elements. And that's what I wanted to say. Mark.
So firstly, thank you, that was a brilliant talk. And I'd love to have many further conversations. Just one thing on this particular diagram, and in relation to what I was saying earlier on about the systems, I think it would be really good to extend this same thinking into a system.
I absolutely agree, and when I saw your presentation this morning, I actually had the impulse to change my slides completely, but it was kind of too late.
Okay, so that's good. What I'm thinking with a systems view is that in many ways the starting point ends up being the use of the system, which is for citizens, for us using the system, maybe as a service. And then a lot of these things are what we do to the system to keep it in use. And maybe it would be good to have have that view in mind of it being a system for human flourishing. That's what it's for.
Yeah.
And all of these things are just interventions in order to keep the system providing the service.
I absolutely agree. Again, there are different kind of levels of purposes. Let's put it that way. Like, for example, when we talk about, let's say, cost estimation, well, that's actually only an intermediate purpose, but in the end we want to reduce costs, or we want to make sure that we remain within the budget that we have, and that's maybe the actual goal. But yeah, you're right.
I just would have one question. I'm a little bit wondering why the digital twin is starting in the conceptual design phase and in the detailed design phase. I would assume or guess that we are talking at this stage of a digital model and not a digital twin.
Yeah. That's a possible interpretation. I would say we are allowed, and that's my interpretation. I think there are as many interpretations here as we have heads. I would say that it would make sense to start creating the digital twin as early as possible, because then you can make the most out of it. So a car manufacturer will start to create his digital twin in the very early phases, and he will use it for producing the car. Yeah, of course you are right, it's a model, but of course a digital twin in the end is an assembly of models. So it's not something completely different. You might argue then it's not a twin because the other twin is missing. And well, if you are very precise, you are correct.
It's a potential twin.
Yeah, it's a twin of the future.
Yes.
But in reality, I have twins. In reality, it doesn't work.
Well, what we have already heard and discussed that according to the application or the usage, we have on one hand different structures, need different structures, different details, different purposes, different semantics. In this case, in case that the twin is for each usage different, then it's very difficult for exchanges. The question is it not possible to define different, let me say, levels or classes of details, classes of semantics, whatever, similar to what we have in CityGML, that we say class number 0, 1, 2, 3 for different purposes. Number 1 is digital elevation models, can be used for different applications, for road planning and so on. Number 2, we have the house in that case and so on. So that to make an exchange possible and easy transferable, that classes for standardization could be defined. What do you think?
I absolutely agree. And I would say that's the only way possible to do it, that we try to organize these use cases, try to see what use case requires what kind of geometry, what kind of semantics, and then have these kind of conformance classes, so to say. And I think, as I said before, the standards that are there already, both in OGC but also in Building Smart, they follow actually this path. So when we now create the IFC tunnel extension, we first define the use cases, and from these use cases we try to identify what would be the elements that are required as extending the IFC standard. And well, I would say that's a good methodology, and we should apply it here as well. Okay, I think my 5 minutes are over, so Jakob, please.